let's talk about acceleration due to gravity. Uh-oh, what's going on here? Oops. There we go. Come on, why do you always do this to me? There we go. All right. Acceleration due to gravity. Okay, so the first thing we need to talk about is the fact that we live on a gigantic sphere, and we call it the Earth. So there it is. Okay, and around the Earth, we experience a gravitational field that will always point in towards the center of the Earth, right? No matter where you go around the world, you're going to be stuck to it, thankfully. Okay? And the reason why this happens is because, now, exactly why it happens, I don't know. But conceptually, the idea is that masses, and the Earth is a big mass, attract other masses, okay? Like rocks or humans or whatever, right? And this mutual attraction, supplies what we know as a gravitational force, okay? So if you put a mass in this area around the Earth, represented by these little arrows, okay? Well, we call this region around the Earth, which actually extends to infinity, but we don't need to get into that right now. We call this Earth's gravitational field. And if something has mass, okay, it is affected by this field and experiences a force. F, we'll call it Fg, the force of gravity, equals mass times acceleration, okay? And close to the Earth in Earth's gravitational field, if you're close to the Earth, this number is more or less set, and we call that acceleration little g. Little g has a value. Is roughly 9.8 meters per second squared. So near the surface of Earth, if you drop something, it will accelerate towards the Earth at 9.8 meters per second squared. Okay, now this value is dependent on a few things. So although the Earth is pretty close to a perfect sphere, we know that if we wander around it, we find things like mountains, right? There's mountains in some places. In other places, there's gorges and whatnots. In other places, there's, big oceans. Oops, can't look at the same color. Right? So part of it has oceans. There's land in other parts. And so on. Okay? And since gravity, right, the attraction of gravity is actually based on the sizes of mass, okay, what this does is it actually causes this value to be a little bit different depending on where you are around the globe, okay? And how exactly that works is a little bit tricky. There's actually a map you can go look at where they've put very sensitive satellites that have mapped the Earth based on its gravitational field. We might actually be able to go take a look at that. Just hang on a sec here. Okay, so I just found this little map, a NASA map here. And basically this is sort of showing the relative, I guess, strength of the gravitational field at different points around the Earth. And we just noticed that where there's mountain ranges, there tends to be a higher field strength, right? And this is because there's more mass there. At least the way I understand that. Here you see a big ridge. I'm thinking probably there's some thick crust there, although I don't know exactly what's going on there. This is probably the deep part of the ocean, or a deeper part of the ocean where maybe the crust is thinner. Okay, so that's kind of the general idea here. So I found a few numbers for you just to kind of show you this variation. At Auckland, which is the capital of New Zealand, you get a value of this if you extend it out to a few more sig figs. Cape Town, South Africa. I don't know why I picked these values. I think I just looked at a big chart and kind of spread them around the world. 796. So these are both not visible on the map. Chicago is 9.803. And London, 9.812 seconds squared. London's up over here. Chicago's here. Okay. Let's find out what it should be where we. Yeah, we're too small of a place to warrant having our field posted, but we'll do an experiment to try to find it. Okay. All right. So it's the last couple of things here before I get you to do some work. We owe this concept of a constant acceleration at a given point on Earth to Galileo. We learned that before Galileo, there was some idea that heavier objects fell faster than lighter objects. Galileo proved that this couldn't. Not only did he prove that it wasn't true, he proved that it didn't make logical sense that it would be true with some interesting thought experiments, which we sort of went over, but that you can sort of look up on your own, and I'll actually put a website in here where you can go to see that. But we'll just give him some credit here. So Galileo proved a few things. Okay. A, all objects accelerate at the same rate, regardless of their mass. And I'm just going to make a caveat. This is when the mass is smaller than the mass of the Earth, like much smaller than the mass of the Earth. If we go to talking about what happens when two planets, say of equal size, are put near each other, what would happen then? That's a whole different story, okay? So we're just going to talk about near the surface of Earth with masses that are small compared to the mass of the Earth, okay? When near Earth, okay? So I know someone out there is going to be like, yeah, but like, what if we like had a black hole on the Earth or something weird like that, right? That's not what we're talking about. We're talking about normal masses, like, you know, the time you drop the chunky soup on your toe, right? That's what we're worried about right now, okay? And B, Galileo did not neglect air resistance, okay? But he was a smart enough guy to say, okay, the reason that we might find some variation, like if I drop a feather and a bowling ball, right, in air, the bowling ball will hit the ground first, right? But Galileo was smart enough to say the reason that happens is due to air resistance, okay? So he, what should I say? He chalked up the previous misconception about weight and falling to air resistance, because air resistance does play a role, all right? So when he was doing experiments with dropping masses, he would like essentially like have a hollow sphere, say, and then one filled with sand or lead or something like that, to even out air resistance between the two, right? As soon as you throw something like a feather in here, okay, you're going to have issues because a feather is light enough that the air resistance forces on it become very great very quickly, okay? The air resistance forces on heavy round spheres take quite a long time before they become heavy enough that they play a role, okay? And let's just talk about that really quickly because people are often interested in this concept of terminal velocity. So let's talk about that just briefly. In air, okay, if we drop an object and it starts to fall, basically there's air in the way of it, right? So gravity is providing a downward force causing this mass to accelerate at g, okay? accelerate down at g. So what that means is after some falling time, the velocity of this object will be higher and higher. In a vacuum, its velocity will just continue to rise, right? So you'll get this. Okay? What will the slope of that line be near the Earth? Challenge question. What will the slope of this line be near the surface of Earth? Right. Reason being is because acceleration is delta v over delta t. So change in velocity over time. Okay, near the surface of Earth, that will work out to g. And we're going to try that with a bit of an experiment. Okay. In reality, though, in air, you kind of get this going on. Okay, where your velocity sort of tapers off to a flat point. And we call this terminal velocity. And the reason that happens is because as you fall, the longer you fall for, the greater air resistance gets. So we'll call this maybe Fd for drag. Okay, and soon Fg and Fd become equal. At that point, no more acceleration is possible because these two forces will cancel out. Why does Fd happen? Well, it happens because basically there's an action-reaction going on. A mass is pushing itself through a thin liquid, if you want, through a gas. And those gas molecules have space between them, right? And as you push them together, you compress them, right? You're compressing the gas ahead of you. They can't get out of the way in time, and so they squash down. A lot like a spring would, okay? And if you push on a spring, well, that spring pushes right back up on you, doesn't it? Okay? You can feel the effect of air resistance in this way. If you were to, say, take a syringe, and you may have played with a syringe as a kid, and, you know, if you seal the bottom of the syringe off, okay, if you plug it, and you compress the air in here, the harder you push, the harder it becomes to push. That's the resistance of air. It's pushing back against this compression. Now, there's ideas of work and so on here that become important, but we'll talk about them later. Another place you might have felt this is if you ever had a BB gun that you could pump. The more you pump it, the harder it gets to pump, or a super soaker even. If you ever had a super soaker, right? As you, this is my drawing of a super soaker. Okay, as you pump air into the super soaker, the more you pump it, right, the more difficult it gets because that air, resists being compressed, and that's exactly what's going on here. People often say this is friction, and there might be some friction, like some of these gas molecules might provide a tiny bit of friction, but the main cause of drag is that compression of air in front. And by the way, as you compress air, it gets hotter. You might know that from chemistry class. And this is why like supersonic jets and so on often have to have some heat shielding on the front. This is also why when spacecraft re-entering Earth from high speed in orbit often experience really high temperatures. It's because they're going really fast and they're smashing into this air, which is providing drag. Compressing that air causes heat, and they heat up. Okay, so that's the concept here. So we get terminal velocity after a while. We've got this concept of g. Let's see if there's anything else we need to cover. No, that should probably do it.